Okay, let's work pathway 7.23. Asks us to use the Rydberg equation for the hydrogen atom model to find the wavelength of a photon emitted when an electron in hydrogen goes from the n equals 5 orbital to the n equals 2 orbital. So we're going from a higher to a lower number, so that's emission. So we would expect a photon of specific energy to be emitted from this hydrogen atom under consideration. Remember, what we're talking about here only applies to the hydrogen atom model, and that's it, including this equation. So this Rydberg equation is presented in your chapter. It is of this form, where 1 over the wavelength in meters is equal to R, which is a constant. It has this value, 1.096776 times 10 to the 7th per meter. And we're going to multiply that R by 1 over N1 squared minus 1 over N2 squared. Now, N1 and N2, what do these have to do with? Do they have something to do with these numbers? In fact, they do. They are, in fact, those numbers where N1 is the lower state and N2 is the higher state. So lower, higher, okay? That assures that this number is going to be, when we do the division, that'll assure that this number is bigger than this one, okay? So it'll work out. We won't get any negative wavelengths or anything of the sort, which wouldn't make sense, okay? All right, so this is our task in hand. We've got to use this equation, set it up, and solve for the wavelength that we would expect to be emitted when we have this n equals 5 to 2 transition. That's what this equation does for us. It predicts the wavelength of light that should be emitted given any transition in specifically hydrogen. Okay? So I'm going to plug in R for my constant, 1.096776 times 10 to the 7th per meter. And then I'm going to set up the math over here. 1 in both numerator. I'm going to square some number, and some other number over here is going to be squared. Now, again, the 1 is the lower state. Which of these is lower? Well, it looks like the 2. So I'm going to put the 2 here, and the higher state is 5. So the 5 goes over here. Now I'm going to square both of them, right? So ultimately what I'm going to do is 1/4 minus 1/25, right? I'm still going to multiply that by my R, 1.096776 times 10 to the 7th. And that's going to equal 1 over my wavelength in meters that I would expect to get for this particular transition, okay? So if I do the math on all that, 1 over wavelength ends up being 2303. This is just my calculator work, 229.6, okay? Now, I'm still not at wavelength. This is sort of reciprocal wavelength, okay? Or inverse wavelength, if you want to call it that. So I got to solve for my wavelength. Now, if I'm doing that algebraically, I suppose I would be forced to multiply both sides by the wavelength to first yield 1 equal to 2303, 229.6 times wavelength times lambda. And of course, if I come over this way, that would mean that my wavelength should be equal to what? 1 divided by 2303, 229.6. And it turns out if you do the math on that, you get 4.3417 times 10 to the minus 7 meters, okay? That's in meters units. Now, the problem, I believe, wants us to report this wavelength in typical way, the typical way or typical units for visible light. And that's typically done in nanometers. It's a convenient unit to use. for visible light. So I need to do a conversion into nanometers from meters. So nano is 10 to the minus ninth, which means there are 10 times 10 to the ninth nanometers, or a billion nanometers in every meter. My meters units cancel. And when I do the conversion, I end up getting 434.17 nanometers for the light that's produced or emitted when the transition of an electron in hydrogen goes from n equals 5 to n equals 2. This would be a pretty blue color light as a result of this transition. Turns out the visible emission lines in hydrogen result when we go from a higher n level to this n equals 2. Okay, if we go all the way down to n equals 1, that's a bigger energy gap, and that usually produces ultraviolet radiation. So the visible lines originate from some higher n level and end up at n equals 2. And that's what Bohr observed.